Welcome back to the workshop. So today, Ferdinand Ihringer from Ghent is going to be talking to us about a few of his favorite things in Erdős-Ko-Rado combinatorics, some interesting variants. So I'll give it to Ferdinand.
Yeah, thank you very much for inviting me and for organizing the workshop. And yeah, I want to talk about some problems related to Erdős-Ko-Rado, which I like and which I find interesting. I hope you will also find at least some of them interesting. And I mostly want to go through a lot of different variants of Erdős-Ko-Rado problems, which are in some sense all a little bit connected. And now I know that this part of the workshop is called Erdős-Ko-Rado for groups. Now, when I want to talk about variants of Erdős-Ko-Rado, the one issue is that usually all Erdős-Ko-Rado problems, at least many, originates just with k-element subsets of an n-element set. So I will mostly talk about k-uniform sets for the variants to introduce the different variants of the problem. I will always quite often use this notation that I have these brackets for the set of elements from 1 to n, because I write it quite often, maybe not too often, but reasonably often, and it always takes up some space to write this. And good, now then, I did not work on Erdős-Ko-Rado for groups in any meaningful way ever, but I work a lot on finite vector spaces. So the other type of structure I want to use as examples for my IKR variants are, here we had k sets of an n-element set, and we say two sets intersect if they meet in at least one element. And the one variant I want to have are k spaces in an n-dimensional finite vector space where two subspaces intersect if they meet in dimension at least one. And lastly, paying attention to the title of this part of the workshop, I will discuss the variants for groups, so mostly the symmetric group and two elements intersect if they have at least one, if this has at least one fixed point. And in general, I try to go through many different variants, and yeah, my choice of references in each set is a bit subjective, I guess. So first, I want to start by discussing nice intersecting families. So we have seen in Karen's talk and in Nathan's talk that the nicest intersecting families are always things like, for sets, all case sets which contain one element. And there are other nice families like that. I mean, here they all intersect because they contain the element 1. We also can have all case sets which contain 2 out of 3 elements, which we fix like 1, 2, 3. Or we have all that contain all case sets which meet some fixed set of t elements in at least t plus 1 over 2 elements. And then they must intersect in there. Now, what do all of these examples have in common? The thing they have in common is that they're all what some people call a junta. Junta, for any family of case sets, not just intersecting families, is a T-junta is a set T with T elements, and we can decide if any of a member of our family is in the family or not just by looking at the intersection of this F with our set T. So here we can decide this by looking at the intersection of the case set with 1, 2, 3. Here by looking at the intersection with the set that contains only 1. And all of these nice intersecting families have the property that they are relatively small juntas. Now, Of course, not all maximal intersecting families are juntas. For example, we can take this example, which is well known to be the second largest example for intersecting family, where we take first all elements, all k sets which contain the first element, and then they must also intersect the next k elements in at least one element. And then we take one element that does not contain the first element. And so here we have one element that we cannot, that does not contain the element 1. And yeah, and now why am I telling you this? I want to give you 3 different perspectives, which you already saw in Nathan's talk yesterday, and to some extent. For example, you can always write the characteristic function of a family seen as a real polynomial in variables, where you have n variables indexed by your n elements, and you say that if you plug in some element of your family f, then it's 1 if the element I is in that set and 0 otherwise. I mean, this is not well defined throughout my talk in a reasonable way, but you can believe me that you can always do that, and that you can always try to find a polynomial that has a minimal degree. Like, it's not unique what you choose there as a function, but you can always find one that is minimal in some sense. Now, the connection to juntas is very straightforward. If something, like for example, if we have our all case sets which contain one fixed element that intersect in family, then we can write this as a degree 1 polynomial. If we have all case sets containing 2 out of the elements 1, 2, 3, then we can write our function as a degree 3 polynomial. So whenever we can decide if something is in the family or not, we have t junta, and we can write it as a polynomial of degree t. Good. Now, we can do the same thing for my other 2 examples, which we have here. For vector spaces, instead of taking the elements of 1, 2, and so on up to n, we can take our one-dimensional subspaces as variables, and we say that, and we can write any family of k-spaces by using these. Here you have a lot of ambiguity how you can do it, but ignore that. And you can do the same thing for permutations, where your variables are if a permutation maps I to j or it does not. Good. And now the last point I want to make before I begin with various problems are the connection to eigenspaces. Nathan discussed that exhaustively yesterday, and I was, as you can see here, I was hoping that Karen and Nathan will discuss that in some degree, how all these nice families correspond to being in nice eigenspaces. And for example, for k-sets, I mean, I did not say that before, that's the Johnson graph. We can order we have k plus 1 eigenspaces of our graph. We can order them in a nice way, and being in the trivial eigenspace, so that is just the span of the all ones vector, is being degree 1. And then being in the first 2 is degree 2, being in the next 2 is in the first 2 is degree 1, and the next 1 is degree 2, and so on. And exactly the same thing also works for vector spaces. So vector spaces and sets behave very similarly. And as we saw in Nathan's talk, for the symmetric group, for instance, there are some differences, like for degree 1, we still have the trivial eigenspace and one non-trivial eigenspace, while for degree 2, we now have 3 non-trivial eigenspaces. And I'm telling you that because at different points, why I like different variants is motivated by this correspondence between these polynomials, eigenspaces, and kind of log families that you can identify locally. So we know the Erdős-Ko-Rado theorem from Karen's talk. We have an intersecting family has size at most n-1 chooses k-1. And we can show this using the ratio bound, which is also called Hofmann's bound or Hofmann-Delsart bound, or sometimes attributed to Lovász. And we see that, as we saw in Karen's talk, we have equality if and only if the characteristic vector of our family lies in the trivial eigenspace plus in some ordering the first non-trivial eigenspace. And we can have equality only in that case. Now, exactly the same thing happens for vector spaces and the symmetric group. So everything there is the same. We have the same type of characterization. Good. Now, first I want to start, if you read my titles about large intersecting families, not only the largest, then I want to go to very small intersecting families, and then I want to leave intersecting families for other topics. So on our way to small intersecting families, the next largest intersecting families are due to Hilton and Milner, and they have size at most n-, this particular size. The particular size is not important, and I think so. And equality, except for some cases, we have when we have the same example that I showed you earlier. So we take all case sets which contain one fixed element 1 and meet the next the elements of 2 to k plus 1 in at least one element, or we have the case set that contains the next k elements, excluding the first one. And actually, this family is still in some sense relatively close to degree 1, because when you write it down, you can write it in a way that you have a degree 1 term and then a few terms of very large degree. And you can actually show that when you project the characteristic vector of this family onto the first eigenspaces, then you still get a very large chunk of them projected onto the trivial eigenspace plus the first eigenspace. So you are still mostly in your first eigenspace, and only a little bit of your family is somewhere else, which also corresponds to the example you have here. Now, there are similar results for the second largest example in various other structures, not in a complete sense, but you have results for vector spaces. Excluding some cases, you have results for permutations. Now, okay, after the second largest example, there are many ways of going to smaller and smaller examples. For example, this result was observed by Dino and Friedgut. It might have been that this is one of the results that was already in some variation already observed by Frankl before. There's always a risk with all Erdős-Ko-Rado results for sets that Frankl already did it. But at least they also observed it. That you can, for an intersecting family, you can find always a star such that a star was something that all contains one element, and you can remove that star from your family and you will get something relatively small. I mean, this is small in the sense because n-1 chooses k-1 is at least when there's enough of a gap between n and k, much bigger. And the important thing here is that the D is a universal constant and does not depend on your N and K. And yeah, the idea is basically the same thing as before. You can use the ratio bound to see that the characteristic vector of a family must be mostly in your trivial eigenspace plus your first eigenspace. And then you know that you can kind of approximate your family by a one runter. Now, here, I think you can say, I mean, Karen or Nathan might correct me if they agree with that, but one result by David Ellis for permutations tells you something very similar. And for vector spaces, getting a vague statement like this is sadly boring for a large amount of parameters, and for the range of parameters which I consider interesting, that would be something like n equals 2k or 2k plus 1. There is not much known, I'm aware of, that is particularly good beyond what you get from the Hilton-Milner theorems. Okay, now we can continue this. Now we know that if we remove a star, then we always get something relatively small, but you can continue doing this game. And there are many ways of investigating smaller and smaller intersecting families. For example, something I will not talk about but want to mention is Peter Frankl and Andrei Kopavsky investigated many degree versions of stability for Erdős-Ko-Rado theorems, which I think are, which is often involves a notion of that is called diversity, which as far as I know, has not been done for the symmetric group, for instance, or I don't know how feasible it is because it relies on techniques which might not work well for the symmetric group. But there's also, from the previous result, you can continue go down this road. If you have a large intersecting family, then you can find some runter. And actually, I forgot to write this here. In this case, it's an intersecting family also. And you can remove this large runter intersecting family out of your family and you get something. What remains is relatively small. Again, the important thing here is that these constants J of R and C of R only depend on your chosen R. It does not depend on your N or K. And so, at least in some sense, you always can say that you can describe large intersecting families, and there are many similar results. I don't want to list all of them, but you can do that. So, the other thing here to mention is that in some sense, all these statements are a bit empty because they always require to be useful that your N is large enough in some sense. Well, maybe that depends on something. So it does not tell you anything about small parameters. Yeah, and so you can describe any relatively large intersecting family as some form of runter, and you know you can take out the runter and what you left will be relatively small. Now, you can investigate the same thing for vector spaces, but there not much has been done, I have to say. And there is, I never read the paper, but there is a preprint by Ellis and Lifshitz, which does something much more general for permutations, so for Sym-N. And there they claim something that is stronger than this result, because it is more general. But you can do the same thing for permutations essentially. Now, that is what we have about still relatively large intersecting families, but not too small yet. And now anything that is a bit larger than, that is a little bit larger, is a junta or a star. So we have a small set of elements which are more important than others, because we can relatively well decide if something is in our family or not by looking at the small subset. Now you can go to the other extreme end of things, and you demand that each element of 1 to n occurs the same amount of times in each of your elements of your family. So that is a regular intersecting family. So what do you have? You count, you fix some I, and you count how many of your k-sets contain that I, and you want that this number you get here is independent of your choice of I. So in other words, what you have is a one design, as that is exactly the same thing. And that is also a nice spectral characterization, namely it means that your family is orthogonal to your first eigenspace. And this is actually a relatively old problem, because Lovász investigated it in 1977. At least I was told so. He investigated it. It's written in Hungarian and it's unpublished. These are at least two reasons why I don't know what actually he did show. But later, Furedi had a much more general result, which is one particular case did show that for a regular intersecting family, you can actually bound the n in terms of k. N is at most k squared minus k plus 1. And he also characterized equality. The characterization of equality was not done by Lovász, but only here. And you have equality if and only if your family is a projective plane of order k minus 1. Now, and of course, you can also show, you can also get bounds on regular intersecting families by using this result we had here. This says if a family is large, then it's a junta. So a regular family does not have a junta, so it must be small. And this is something I wrote up with Andrzej Kupawski not too long ago. And we also collected a long list of other small results on regular intersecting families for sets. For example, you can modify the ratio bound slightly. I mean, now you know that all your examples must be orthogonal to a certain eigenspace. And you get actually a bound that does not seem to be too bad for n equals 2k plus 1. Now, the problem is when you want to generalize this property to other structures, then you can quite easily see that you can never satisfy this condition of being orthogonal to this special eigenspace here. And you cannot do so in vector spaces. There you have no regular intersecting families, and as far as I can tell, the same happens for permutations. There I must admit that I only checked it for small n, that it's impossible, but I don't see why it should change when n is large. Now, at the end of my talk, I will suggest a reasonable generalization of regular intersecting family to the symmetric group as a possible problem. Now, what is also recently quite popular are symmetric intersecting families. That is a special case of regular intersecting families. Here we now want the automorphism group of our family to be transitive on our elements. And David Ellis, Gil Kalai, and Narayanan did investigate this at great length. I want to add here that, usually you are wondering if regular and symmetric are the same thing or not. And actually here, at least for a certain range of parameters, the behavior between regular and symmetric is very different. Because just together with Andre, we constructed examples that for regular intersecting families that are larger than an upper bound they have for symmetric intersecting families. And the notion of symmetric intersecting families is also investigated, for example, for the hypercube or the Hamming graph. Even so, there you lose most of your connection to any spectral properties that we had earlier. But you still have the nice property that all your best constructions in some sense seem to come from projective planes, if they exist. This is not a theorem, this is just the best thing people know. It might not be true. Good. So much about small intersecting families. Now, let us move on to another bound, which, if I remember correctly, Karen mentioned in her talk, which I was hoping when I prepared the slides, namely the co-click bound. And let us just state it again in a very, very specific case. You have an intersecting family, and here we have k sets in an element set, and we want that k divides n. And your other family G is just a partition of n into k sets. And then what you can show is that the cardinality of f times the cardinality of G is at most the number of k sets you have. And that you can show by using a simple double counting argument when you know that such an f and that G can intersect in at most one, it can have at least one member in common. Otherwise, we have two disjoint sets in F. So we have this inequality, but we can move our G around, and this will always happen. And you can write down a nice double counting argument, and you will see that this implies this inequality here. Now, so that is the co-click bound, and a very natural generalization of that co-click bound is, here we have that F and G intersecting at most one element. But we can also, instead of at most one, we can say at most S. That means that in F we have at most S pairwise disjoint sets. So it makes sense that we say that a matching of F has at most size S. And of course, if S equals to 1, then we just have an intersecting family. Now, using exactly the same argument, again here, because it's convenient for only k divides n, you will see that F and any partition into k sets intersect in at most S elements. And if you use the same argument you can use here, then you will get that the size of F is at most S times n-1 chooses k-1, so S times the size of intersecting family of maximal size. Good. Now, there are two nice examples for such families, and they never reach this bound except for S equals 1. So one example is we take all k sets which intersect the first S elements non-trivially of course, they must all contain an element of the first S element, so you cannot have S plus 1 pairwise disjoint k-sets in your family if you do that. Now, you can also take all k-sets, I mean, that's the other obvious thing to do, that are contained in the first S plus 1 times k minus 1 elements. And you cannot have S plus 1 disjoint k-sets in there. And Paul Erdős conjectured a long time ago that these are the largest, or at least people say it's a conjecture. He had a very nice phrase. He said it is not impossible that one of these is always the largest family. And his notation is slightly different, but you can see that this corresponds to the family 2. Maybe I could, no, I don't want to play too much with colors, but like this is family 2 and the other one is family 1. And he actually did show it for some cases. Now, this is still connected to all the things I told you before. For example, a relatively reasonable approximation of our first family, which is the only family I will care about in the following, is that we just have the polynomial, which is just the sum of the first S elements. And as soon as n is far enough away from k times S, that's a reasonable approximation. Good. Now, so this is a very natural generalization of Erdős-Ko-Rado. And I only care here about the case where n is relatively large, so that the first family is always larger. And that problem had, I mean, it was around for a long time, and over many decades, the bounds were improved further and further. Like Erdős originally did show that his conjecture is true starting at some constant depending on k and s. Then slowly this became more specific. Instead of having this vague expression, you have a 2k cubed times s. Then there is an unpublished result by Frankel and Furedi, where you have, which is linear in k, but you have an s squared. But that was not published. I think they did this in the early 90s, but I'm not sure. And then it became very popular at the beginning of the last decade. Huang, Lu, and Sudakov replaced the cubed here by a squared. And later, Frankel replaced the squared here with a 1. Maybe I should put a 1 here. And 2 times s plus 1 in front. And if you don't care about small s, then Frankel and Kupowski did show that you can find some universal constant. Is it universal? Maybe it depends on something, but when s is larger than that, then you can actually have a factor of 5/3 here. Good. Now, what is some generic way of investigating such intersecting families? One idea that you can always use is you try to find a large, like of these Erdős matching conjecture families. One idea is that when your n is large enough compared to something, you can always try to find a relatively large intersecting family. You can take that out, and then you go from S to S minus 1, for instance, and then you can continue doing induction. And another thing that is actually quite useful is to investigate the intersection with partitions or fractional partitions or all kinds of variations. The last result here uses a nice concentration inequality. I investigated this in case of vector spaces because I wanted to actually I care about something different, which will be the last part of my talk, but you can also investigate the same kind of problem for vector spaces, and then you obtain some bound. And you can also state a very similar conjecture, just the conjecture of vector spaces is more complicated to state. And actually, I cared about it because I wanted to explore families that are close to degree 1 in vector spaces. Now, the sad thing for the topic of the workshop is that the problem is very boring for the symmetric group. Namely, we always have derangements in the symmetric group. So using the same bound I showed you before, the click-co-click bound, we always see that a family with matching number S has at most this size. But it's also trivial to construct such families. We can just take all permutations which map 1 to one of the first S elements. These families are all don't share a common element, so we can just obtain equality. But it might be interesting to look at smaller groups. For example, there are groups where this argument for the bound stops working, then of course it becomes interesting, or when you can no longer easily obtain equality, for which I think it's helpful that you, instead of having a notion of, like here, always have 1 intersecting, having some notion of t intersecting, or using the equivalent thing for t intersecting seems to be the better thing to do. Good. So figuring out what might be a good open problem here is an open problem. Now, the last part I want to talk about are now what I would call here low degree Boolean functions. So we saw we can always write a family, any family of k sets, as a real polynomial of some of degree at most k. We can, and that corresponds to just being in the first k plus 1 eigenspaces in a certain, or in the first, if we write it as degree d, then it's just being up to the dth eigenspace here. And in all the examples I discussed for large intersecting families or relatively large intersecting families, we saw that being large as an intersecting family corresponds to having relative low degree, or being sitting somewhere here in the eigenspaces mostly, and not having much in the remaining eigenspaces. That's also something Nathan talked about yesterday. And the same thing happens for the Erdős Matching Conjecture, that all your examples are mostly sitting in these eigenspaces and not in the remaining eigenspaces. And now one can ask in general, what is the structure of these polynomials of low degree? And this is actually investigated for a long time for the hypercube, because it's interesting for very different reasons. So it's the same notion as before, but as for sets where you can easily see that all your affine functions are either constant or they only depend on exactly 1 coordinate if they are of degree 1. There is a famous Fkn theorem which did show that, whenever I write almost, it differs what I mean by almost, and it's always something asymptotic which I don't want to define. And they did show that if you make your n here large enough, then you can then any Boolean degree 1 function, so any it means these are real polynomials, but they always have, if you put something into them, they always return 0 or 1. They must be either constant or they only depend on exactly one input, and when it's almost degree 1, you can use these guys to approximate them in a good way. And there are similar things in more generality. For example, a Boolean degree D function one can show is always a Junta, so you can make your n arbitrarily large, but you always know if you have a degree D function for fixed D will only depend on a fixed number of elements. And you can always say the same for almost degree D. So this is something that was investigated for a long time. And you can always investigate the same questions for the structures I'm discussing, like for case sets. I mean, some of these questions are interesting for many, many different reasons. For instance, there are many reasons why you find functions that sit in the first in the trivial eigenspace plus the first eigenspace interesting. And then you can show it's for case sets, it must be constant or it must be the same. It only depends on one coordinate. I think you need some restriction here, like n minus k and k have to be at least 2. Otherwise, that's not true. And this was shown many times independently, usually as an example motivating a more general result. Now, you can also say something about almost degree 1 functions. Here, the behavior is a bit different compared to the hypercube case. You have, but you can still use these guys here to approximate them by looking at you can always write something as Boolean almost degree 1 by a sum of these xi and 1 minus xi. And here are some extra conditions on the whole thing, which I do not want to get into. And you can also repeat the previous results. Whenever you have a Boolean degree D function, then you know that you have a Junta. So yeah, you can decide, you can approximate it well. You can actually decide containment in your family or not by looking at the small subsets of your n elements and how your set intersects the small subset. Again, this fails when k or n minus k is too small. Now, and you can also do the same thing for almost degree D. Okay, now for the symmetric group, again, it's now a bit repetitive. You can do similar things. You know that for the symmetric group, Alice Friedgut and Pilpel did show that it's a disjoint union of all the permutations that map. So for example, you have all that maps 1 to 2, and you have all that maps 1 to 4. And these are all the types of degree 1 functions you can get. And with a small permutation with a small change in names, like you still have Friedgut, you still have Alice, but now you no longer have Pilpel, but you have Filmus. You can have a result that an almost degree 1 function is close to a union of these guys. Now, Nathan Lindsay, Yuval Filmus, and others did show now very recently. Actually, he did not talk about this, so I can cross out the sentence here. That generally you have a degree D function in this context. You can have some kind of decision tree to describe the function in a certain way, or an almost degree D function. He talked about this in the algebraic combinatoric seminar. And yeah, so for the symmetric group, you also have the same list of results. Now, what is open here? I mean, I never thought about this, but I have no idea if you can say anything about smaller groups, like even what are the Boolean degree 1 functions in that context. So this is usually just what sits in a certain eigenspace. So you can also see it as a regular set of certain graphs, which is a different way of looking at it. Now, where the whole thing is interesting, I think, particularly interesting are vector spaces, because now there are interesting things happen, at least in some cases. So if we have case spaces of an n-dimensional vector space, our variables here are the one-dimensional subspaces, but we also want to write them for n-1 dimensional subspaces and hyperplanes, where the problem is known as Cameron-Liebler line classes, which was motivated by questions in group theory that Cameron and Liebler investigated. But these Cameron-Liebler line classes in this context correspond exactly to degree 1 functions or Boolean degree 1 functions or things sitting in this eigenspace. So there are many ways why you might find them interesting. And as before, you have a list of canonical examples that seem natural to look at. For example, you can take all case spaces which contain a fixed one-dimensional subspace. You can take all case spaces which lie in a hyperplane, and I can write them in this short way in the same format as I had before, as degree 1 polynomials. And you can also take one-dimensional subspace, which I think projectively, so for me it's a point and a hyperplane, which are not incident with each other. And you can take all case spaces on that point and all case spaces in that hyperplane, and you have another example for something of degree 1. And of course, as before, you can always take complements. And Cameron and Liebler made a lot of, I think, 3 different conjectures. I must say all their conjectures were for k equals 2. And they assumed that there are no other examples except these 3. And this conjecture turned out to be, I mean, some of the conjectures they had were correct, I think, but this particular conjecture turned out to be false. I mean, at least it turned out to be false for the case that n equals 4 and k equals 2. And there's a conjecture by Cameron and Liebler is wrong. Now you found more examples. When someone makes a wrong conjecture and you find examples contradicting the conjecture, what do? You name the counter examples after the people. So these things are called Cameron-Liebler line classes in this particular case. So it's sometimes good to make false conjectures because then things get named after you. And you have nowadays a very, very long list of various different counterexamples for this conjecture. In the particular case, I cannot overemphasize this only for k equals 2 and n equals 4, but for any prime power larger than 2, I think. Maybe not all, maybe you skip a few even prime powers, but you have a lot of counterexamples. And now, so this was all for n equals 4. If we go for n larger than 4, the whole thing is very different. Namely, you do not find any more examples as soon as that is the case. And this was shown iteratively for q equals 2 and 3 by Drudge, for q equals 4 by Gavrilyuk and Mogilnik, and then for q equals 5 again by Sasha Gavrilyuk and Matkin. And they did show that all Cameron-Liebler line classes are only the easy examples that you can easily find, nothing complicated. That is very different to this case. And now how you do that is you do induction on n. Now you can also start doing induction on k. And when you start doing induction on k, you see that this is also true for all k as long as n is larger than 4. And it is the restriction here is you have only q equals 2, 3, 4 and 5, and it could be that this is no longer true as soon as Q is larger. But the natural conjecture here, or an open problem, would be to show that it actually works for all, that this is true for all prime powers. Now, what about the other problems for vector spaces? Obviously, if you cannot even determine what has degree 1, having almost degree 1, degree D, or almost degree is hopeless. And it's also not clear how you would best define almost here. That's a problem on its own. But I want to conclude my talk with mentioning that investigating these things is interesting for other things. For example, not too long ago, there was a proof of the Unix games conjecture, which is a conjecture that, don't ask me exactly what it is. I understood it once some time ago, but I always forget it again and again. It's something about approximating specific and p-hard problems, and not the Unix games conjecture, but the 2-to-2 games conjecture was proven by Coate-Mintzer and Safra. And they actually investigated certain families of K-spaces in a binary vector space, which have, I mean, to adopt Nathan's terminology from yesterday, significant Fourier weight or mass on low degree. And they did show that these families, I mean, what they showed is that you have subspaces A and B, and you find that between these two subspaces, you find a lot of the family. So it's somehow kind of more local. And this was with a long list of implications implied this result here. And they wrote a long paper showing exactly that. Now my time is up. I have some open problems which I added just yesterday because everyone had lists of open problems. I have one suggestion for regular intersecting families on the symmetric group, which I think is slightly different to what Karen suggested the other day. Yeah, thank you for your attention.
Let's thank our speaker. All right, any questions?
Can I ask a question?
Go for it.
Okay, I actually have to run in just 5 minutes, but Ferdinand, how do you, it's sort of a question about how you define your T functions for the permutation group, like your low degree spaces. I'm saying it all wrong right now. Like in your talk, you said they were corresponded to the eigenspaces that have the partition is the n minus t and then whatever else. But there's a little bit of flexibility on how you define the low dimensional spaces. Do you know what I mean? I'm saying all the wrong words.
So I think Ferdinand was including all the other, so.
All of them, right?
Yeah,
like,
all of them, yeah.
The first part is n minus t, and then all the different partitions.
Yes.
But you don't, you'd have some choice about that. Like if you're looking at the two setwise intersecting, the modules you'd care about would be the n minus 1, 1, and the n minus 2, 2, and you wouldn't want to have the n minus 2, 1, 1 as well. And that you could describe that with the degree 2 polynomial.
Yeah.
So how do you define what, when you're looking at permutations, do you have sort of a set rule of how you're defining? Maybe what I want to say is that there's more than one, you have some options about what space you're looking at. What is the word I'm looking for?
I think, correct me if I'm wrong here, Ferdinand, but I think
he was a better person to answer that, but yeah, just, yeah.
Yeah, so if you when you go to polynomial land and you start representing these intersecting, like say canonically intersecting families as polynomials, then you really do need that like that, for instance, that n-2, 1, 1 space for like say the canonically two intersecting families of the symmetric group, because you can just show that it has some whatever you want to call it, Fourier mass sitting on there. But like for this variant that you're talking about, yeah, it could very well be that it's just orthogonal to that space and you don't need it. And then you can have a sort of a different definition for like the setwise case. But I think it's useful to think about it, I guess, devoid of like a particular sort of combinatorial problem. Like it's just like these things are just kind of like these things are just polynomial spaces that live out there, and like there's, as far as I know, there's only one natural way of saying what a degree T polynomial is on the symmetric group, and it's exactly as Ferdinand described it. You have like an indicator variable for each edge or for each mapping, like if I goes to J, and so.
But when
yeah.
you switch up your polynomial, you might get different spaces. Like,
yeah, but when you have the indicator variables, how I said it, and you then look at the squares of, it's a product of two of them, then it's just that it's the eigenspaces you get is what I said as a notion of degree.
but what if you took the polynomial where 1 goes to 1 times 2 goes to 2 plus 1 goes to 2 and 2 goes to 1. I'm looking at the setwise.
Yeah, so in that case, right, it'll be, we would say that's in the degree 2 subspace, but it's not like, it doesn't span the degree 2 subspace. So because like if you took the span of all degree 2 polynomials, then that would span the space n-1, 1, n-2, 2, and then n-2, 1, 1. But like if you start like adding these things together and things like that, you'll get some like you can come up with polynomials that are orthogonal to say like that last subspace. Is that what you're asking, Karen?
I think you answered exactly in that the space is the span of all degree 2.
Yeah.
Okay. Sorry, I have to go to another meeting that I'll be in trouble at if I'm late. But thanks very much.
See you, Karen.
Yeah, see you.
Any other questions? So maybe if we don't have any other questions, can you say more about the open problem that we have here that's emphasized?
I mean, I emphasized it because it's different to how Karen defined it, and now she is gone. But I can say, so like if you want to define regularity for intersecting families in the symmetric group, then at least for small n, I did not try to look at it for general n, but I guess it's true in general if you just want that it's orthogonal to, I guess, this eigenspace, then there are no intersecting families orthogonal to that eigenspace, which you can see by looking at the projection onto that eigenspace. So you have to define it in some way that you can still find examples.
Yeah.
But that you still have the property that you prevent your families from being, like you still want to have some kind of regularity. And I think you also want some kind of regularity which makes it in line with the other problems. Which puts it like with the other problems, so it forces your family to be very, very small. And the way the problem is that you can no longer think about it in spectrally too much, I think. But the way here I define constants aij, And maybe I should just make a stupid example where, so what we want is, we want a I being always equal to some constant a. So the number of things that map I to j, to I, and aij is equal to some constant b for I not equal to j. Of course, this is no bad definition because we can just apply some permutation to all our elements, and then it's no longer regular intersecting in this sense. And that is why I have this sigma up here. Oh, I have a different symbol here. That is a typo. That happens when
okay.
I add stuff one day in it. Add stuff only one day earlier. And so this is the largest. I mean, instead of just having one number here, like for regular intersecting, you have now two numbers. And it's also in a way that you, like, if you do not have, and if you're not careful with that, then you still include the largest example. Like if you just want that you have only two constants here, then you can still take everything that maps I to I, let's say, and then you have also only two numbers. So what is important here is that you have, like, everything on the diagonal is one number, everything on the off diagonal is one number essentially. And the other nice thing is it corresponds to all the other variants of the problem for regular and symmetric intersecting families, namely that the best thing I can think of are projective planes and stabilizing lights of a projective plane. And that is also what other people for the other problems is the best thing they can think of. So it seems to be in line with the other problems.
Yeah. Yeah, it's interesting. I like it because it's seems like it's forcing us to get away from the ratio bound, and well, I think that it's definitely something that maybe we're guilty of using too much for solving some of these problems.
But I hope it also makes things again somehow easy because you have a lot of regularity you can try to use.
Yeah, yeah.
It's not like when you try to do something slightly away from the ratio bound, where you still use the ratio bound in some modified version to get something for that. Like the Alice Liefschitz preprint, for example,